Hello, welcome in the third lecture of convective heat transfer. In the previous lecture, we have learnt about derivation of thermal energy balance equation. We have seen there how thermal energy balance equation can be written in terms of internal energy equation and enthalpy balanced equation. From that same point, we will be continuing over here and we will see some other forms of internal energy balance equation over here. So, our topic for this one lecture is different forms of thermal energy balance equation. So, as I will be continuing from the previous lecture, I will be following the same equation numbering over here in this lecture. So, please refer to the previous lecture for the previous portions. Okay, let us see what will be the outline of this lecture. At the beginning, we will be recapitulation of the equations whatever we have covered in the previous lecture. Okay. So, we will be showing you the final form of thermal energy balance equation, okay, in the internal energy balance form and enthalpy balance form. Okay. We will be using TDS equation over here for derivation of entropy balance, okay, equation. So, not entropy balance, I should say the thermal energy balance equation in the form of entropy. Okay. Then we will be using Maxwell's relationship, okay, to obtain thermal energy balance equation using CV. Okay. Also, towards the end we will be converting CV form of thermal energy balance equation to CP form of thermal energy balance equation. Here also we will be starting from conservation of thermal energy balance equation, and from there using Maxwell's relationship we will be bringing that equation into simplified form using CP, right. Okay, so let us first go to the content of the previous lecture. In the previous lecture, we have actually described the balance of total energy for a closed system. So, this came in this form. In the left hand side, we are having the rate of change of energy in storage, and in the right hand side, we are having the energies in transit. First one is energy due to heat transfer, and second one is energy due to body force, okay, which is nothing but work done due to body force, and third term is actually work done due to surface forces. Okay. Then we have actually subtracted from this total energy balance equation our mechanical energy balance equation, and we have obtained our thermal energy balance equation. So, this is balance of thermal energy. So, we get in the left hand side we are having rho into dE dt, and in the right hand side your energy in transit due to heat transfer will be remaining, and this is nothing but your deviatoric part. So, you will be having tau Ji into del xj of Ui. Okay. Next, we have also shown that how viscous dissipation pi Ji into Dij, which is nothing but your deformation tensor. In between we have also said that rotational tensor is antisymmetric, that can be cancelled. So, this last term of this thermal energy balance equation, which is the deviatoric part, that has simplified to pi Ji into Dij, and that we have showed for Newtonian fluid how that can be connected with thermophysical property mu, okay, over here and here. We have also derived further and shown that how this equation can be casted in terms of internal energy balance equation. So, here you see E is the internal energy, okay. The term which was there as pi Ji into Dij, that we have kept here as phi, and we call that one as viscous dissipation. Okay. Also, this equation we have recasted once again, and we have expressed this thermal energy balance equation in the form of enthalpy. So, here you see H is the enthalpy. Okay. Some changes in the right hand side occurred due to the change of E to H. Okay. We have done that using the relationship between E and H in the previous lecture. Okay. So, from this point we will be continuing in this lecture. So, in this lecture we will start first conversion of this thermal energy balance equation into entropy based balance of thermal energy equation. Okay. So, from basic thermodynamics, okay, we know that TDS relationship is like this, TdS equals to dH minus V dP. Okay. So, here you see in the right hand side we have enthalpy and left hand side we are having entropy. So, this equation we will be using for shifting this enthalpy based equation to entropy based equation. Okay. Now, from here we can write down once again TdS by dt by making derivative with respect to time. So, TdS by dt is equals to dH dt minus of V del t of p, right. So, if we proceed further, then we can see by doing little bit of change of sides, we can write down dH dt equals to TdS t ddt of S plus of V into ddt of p. Okay. From this equation, little bit change of sides, we can obtain this one. Next, multiply rho in both sides. Okay. So, you will be getting rho is being multiplied both sides. Okay. So, equation comes in this form. Here you see I have converted small d dt to capital D dt, total derivative. For some purpose I will be explaining later on. Next, from enthalpy balance equation, whatever we have actually shown you in the last lecture, you can get that rho into d dt of h. See, I have used in the last lecture capital D dt total derivative. So, here also I have actually shifted from this small d dt to capital D dt. Okay. So, in our last lecture we have shown that enthalpy form of balance of thermal energy equation is like this, rho into dH dt is equals to minus of del q plus d dt of p plus of phi, phi was the viscous dissipation. Now, in left hand side we had rho into dH dt or rho into d dt of h, which is equivalent to this one. From basic TdS equations we have proved that this can be linked up with d dt of S, entropy, right. So, we will be shifting it over here, okay, in the left hand side. So, if you do that, then you will be finding out this dp dt can be cancelled out, because rho and v, they are reciprocal to each other. So, rho and v can be cancelled out, and we got one dp dt in the left hand side of this equation, and right hand side we are having dp dt. So, this term from both the sides can be cancelled, and you finally obtain rho into t of d dt of S is equals to minus of del q plus phi, phi is the viscous dissipation. So, in this equation you see we have once again done the balance of energies, thermal energies rather, but here this we have expressed in terms of S, which is nothing but entropy, right. So, in the left hand side we are having actually rate of change of energy in storage in the form of entropy. In the right hand side we are having first term is actually your energy in transit via heat transfer, and next one is actually viscous dissipation, right. Okay. So, this equation we will be calling as entropy form of balance of thermal energy equation. So, this is very very important vital equation, entropy form of the thermal energy balance equation. So, till now we have seen internal energy balance equation or energy balance equation in the form of internal energy balance equation in the form of enthalpy, and today I have shown you energy balance equation in the form of entropy. Next, let us see some other forms. So, first I will be going for thermal energy balance equation in the form of CV. Okay. So, derivation of CV form of conservation of thermal energy balance, right. So, we will start this derivation from this one, that internal energy E can be written as function of temperature and volume T comma V, right. So, if I write down like this, and then if we try to find out the derivative of E as it is function of T and V, this can be written as del T of E at constant V into dt plus del V of E at constant T into dV, right, because it was function of T and V only. Okay. And here in this side we are having you see the first term is actually del T of E, that means what amount of energy you require to change the temperature per unit degree. Okay. I am not mentioning about unit because here we are having dt, so that is unitless. So, per unit degree change of temperature, what amount of energy is required at constant volume. So, you can relate that is equivalent to your CV. So, I can write down CV, Okay. So, this is dE equals to CV into dt will be remaining as it is, and second term for the time being we have kept as it is over here. Okay. So, we have got dE is equals to CV into dt plus of del V of E at constant temperature into dV. Now, let us do something else. Let us start from once again our very famous thermodynamic relationship TdS equation. So, TdS equals to dE plus PdV. Okay. This all of we know from thermodynamics prerequisite. Then what we will be doing, a little bit change of sign and then divide by del V. If we do, then we can find out del V of E at constant temperature is equals to T into del V of S at constant temperature minus P. Okay. So, I have actually taken this term in the left hand side, this term in the right hand side, divided by del V, and over the whole equation I have kept the temperature constant. So, this equation appears, right. Next, let us use some Maxwell relation to convert this term into some other known form. So, if we do that, we can write down one of the famous Maxwell relationship is like this: del V of S at constant T is actually del T of P at constant V. So, you see here we are having this del V of S at constant T, we can substitute that one by del T of P at constant V, right. So, if we do so, we get this form. So, del V of E at constant T is equals to T into del T of P at constant V minus P. Okay. So, this term we have actually got from Maxwell's relation. Okay. Next, if we just put this final form over here, okay, if we put this final form over here, then we will be getting this equation. So, dE is equals to CV into dt plus T into del T of P at constant V minus of P and whole multiplied by dV. Okay. Let us now do it further. So, what I am doing over here, we are having dV over here, we are actually writing down that dV is equals to minus of 1 by rho square into d rho, because V is equals to 1 by rho. Okay. Specific volume is equals to 1 by density. So, we are writing this one. So, this has changed sign over here inside this third bracket, and we have written in terms of dV d rho by rho square, right. So, if we do it further, so dE by dt, so here also I have converted this small d to capital D just to match with the previous slide. So, this ddt of E is actually CV into ddt of small t. Here small t is time, capital T is the temperature, plus this term remain as it is, 1 by rho square I have kept, d rho by dt will be coming. Okay. So, if you remember, our internal energy form of thermal energy balance equation was like this. Okay. So, in this we had d rho ddt of E in the left hand side, okay, which was nothing but rate of change of energy in storage. Okay. So, here I have obtained some form of ddt of small e. So, I want to substitute this left hand side, whatever I have got here in the right hand side of this equation, to this equation whatever we have obtained in the previous class for internal energy form of thermal energy balance equation. So, if we do so, then we get, you see, so this term is nothing but rho multiplied by the left hand side term of this equation. Okay. And here in the right hand side we are having all the energy in transits. First one is actually due to your heat transfer, second one is hydrostatic part, and third one is actually deviatoric part, right. So, if we simplify it further, then we can find out that over here this term whatever we had 1 by rho into ddt of rho, from continuity equation we can write down this is nothing but minus of divergence of u. Okay. So, once I write down this is minus of divergence of u, I get P into del u, okay, in the left hand side. I had P into del u in the right hand side also. So, those can be cancelled. So, you get finally the simplified form as rho into Cv into dt plus this term and this term will be coming here, T into del T of P at constant volume into divergence of u. heat transfer, rate of change of heat transfer will be remaining in the right hand side and viscous dissipation will be remaining over here. Hydrostatic part already I have cancelled from both the sides. Okay. Then you see, if we take this second term of the left hand side in the right hand side, so you get rho into CV into dt, which is nothing but a CV form. In the right hand side, in place of del q, I can write down del of k into delta t. So, q I am writing k into delta t. This is by following the Fourier's law of heat conduction. Okay. And then this second term in the left hand side actually came in the right hand side over here with a minus sign, plus viscous dissipation remains over here. Right. Here it is important to mention this k is nothing but the thermal conductivity. Right. So, you see this equation can be called as CV form, because CV is involved over here, CV form of conservation of thermal energy balance. Okay. So, this is very important equation, please remember this one. Next, let us see that can we convert this one into CP form. Okay. CP is nothing but specific heat at constant pressure. Okay. In the previous one we have converted that one into specific heat at constant volume. So, here let us see that can we convert this thermal energy balance equation in CP form or not. To start with, we will once again do just like the previous one. In the previous one we have written E as a function of temperature and volume. Here let us write down H as a function of temperature and pressure. Okay. And we almost follow the same analogy to make the derivative of H as dH equals to del T of H at constant P into dt and del P of H at constant T into dP, right. So, here also this del T of H at constant P, which is nothing but per unit degree change of temperature, okay, what amount of energy is required H at constant pressure, which is nothing but our Cp. Okay. So, here I have written this term as Cp. So, this is Cp into dt plus of this term remain as it is del P of H at constant T dP, right. So, we have got dH equals to Cp into dt plus del P of H at constant T into dP. Okay, next let us use once again our famous thermodynamic equation TdS now, but now this time we will be using with dH. So, TdS equals to dH minus VdP. Okay. If you remember in the previous description CV form, we have used TdS equals to dE plus PdV. Here we are using TdS equals to dH minus VdP. Okay. Next, now here you see we are dividing this equation, famous thermodynamic equation, both the sides by dP. So, we get TdS dP. So, T ddP of S is equals to ddP of H minus V. Okay. So, this equation if we do a little bit of side change, okay, so that means side change means this you take in the left side, this you take in the right hand side. So, you are getting this equation. Okay. So, ddP of H at constant T is equals to T into ddP of S at constant T plus V, right. Next, once again try to use Maxwell's relation and convert this term into some other form. So, if we do so, one famous Maxwell relationship we will be using, which is nothing but del P of S at constant temperature is equivalent to minus, important, very important, minus del T of P at constant V. Okay, sorry, del T of V at constant P, right. So, here you see if I can substitute this term over here. So, this term will be coming over here with multiplication of T. Next, you see here I have written del P of H at constant T is equals to T, but this minus came over here. So, minus T into del T of V at constant P. So, I have used the Maxwell relationship over here, substituted this by this with a minus sign plus V. Okay. Little bit of modification. What we are doing over here, we are taking V common from the right hand side. So, if you take a V out of this two terms, so V comes over here. From the first term there was no V, so this is actually minus of 1 by V into del T of V at constant P. T will be remaining as usual, plus here was V. So, as I have taken V out, so this will be plus 1. Okay. Now, this term is actually can be written as beta. Okay. So, what is beta? Beta is nothing but per unit degree change of temperature, how much amount of volume is being changed at constant pressure per unit volume. Okay. So, that one I am writing as beta, okay, volume expansivity at constant pressure, right. So, if I write down this one beta, this whole term, then I get del P of H at constant T is actually V into 1 minus beta into T, right. Okay, then here I have once again showed that what is the expression of beta over here, which we have used. Okay. Then we can write down dH, which I have already showed you over here. Over here you see I have showed you dH is equals to Cp into dt plus of del H del P at constant T into dP. So, this term I am now replacing with del H by del P at constant T is equals to V into 1 minus beta into T, and then finally I get dH is equals to Cp into dt plus of 1 minus beta T into dP by rho. Okay. Next, this dP into rho, whatever we have got there, I try to take this rho in this side. So, rho dH. So, you see first I have divided by dt both the sides, okay, and then I have actually tried to put this equation multiplied by rho. So, if you take multiplication of rho from both the sides, so you will be finding out this rho will be cancelling out. So, this is becoming 1 minus beta T into dP into dt of P, right. Then we know that in the enthalpy form of our thermal energy balance equation, left hand side we had rho into ddt of H. So, let us put this whole term in the thermal energy balance equation, which is having H form, okay, and we get in the left hand side I have substituted this rho into ddt of H with this term, and right hand side we are having same as usual minus of del Q plus of ddt of P plus of the viscous dissipation phi. So, we get this equation where Cp is involved. So, little bit of simplification will be giving me the Cp form of our thermal energy balance equation. So, if you see over here, here we are getting one dP dt in the left hand side, okay, 1 into dP dt, and right hand side we are also having dP dt, which can be cancelled out by doing simplification. So, if you do so, then you will be getting rho Cp dt dt in the left hand side. Let us take this beta T into dP dt in the right hand side. So, beta T into dP dt came as the first term in the right hand side. Here we had minus del Q. So, that minus del Q we can write down as Q is nothing but minus of K into delta T. I have told you just now that this is by Fourier's law of heat conduction. So, that can be written as del dot K into delta T, okay, and finally the phi remains over here as viscous dissipation. So, you see here this is also one energy balance, thermal energy balance equation. In the left hand side we are having the Cp form, okay. So, this equation is also very important and known as Cp form of balance of thermal energy. Okay. So, what we have seen that at the beginning we have converted our energy balance equation, thermal energy balance equation in entropy form, and then we have got two important forms, one is CV form and another one is CP form over here, okay, involving CV and CP respectively. Okay. So, these three forms newly we have learnt in this lecture. And in the previous lecture we have seen two more forms, one is internal energy form, another one is enthalpy form. Okay. So, let us summarize this lecture. So, what we have done, extrapolated the knowledge of enthalpy and internal energy balanced energy equation, which I have dealt in the previous lecture, and found out or developed entropy based balance of thermal energy equation. So, this came as final form, I have showed you already. And we have also tried to see specific heat based thermal energy equations, specific heat at constant volume and specific heat at constant pressure. So, this was the final form for the specific heat based equation at constant volume, and this was the final form of specific heat based thermal energy balance equation at constant pressure involving CV and CP respectively. Okay. So, we have dealt with 5 different forms. So, first we have seen internal energy form, then we have seen enthalpy form, and today we have seen the entropy, CV and CP forms over here. So, at the end of this lecture, let us once again test your understanding what you have learnt over here. We are having 3 questions over here for you, which is having actually multiple answers. You have to pick up the correct one. Let us see the first one. In the first one, you have to find out the correct term which expresses CV, okay, from the thermal energy equation. So, we are having 4 options over here: beta T into del T of P, ddt of P, okay, minus T into del T of P at constant volume multiplied by divergence of U, ddt of P, and fourth option is minus P into divergence of U. Okay. So, these 4 options, you know what is the correct one. So, the correct one will be obviously option B, okay, minus T del T of P at constant V multiplied by del dot U, right. Next question goes like this: for open system, which form of thermal energy equation is most suitable? I should not say suitable, this is the most suitable. Okay. We have seen 5 different forms. Out of that, we are having options as CV form, entropy form, internal energy form, and finally enthalpy form. Okay. So, all of you have probably guessed from your basic knowledge of thermodynamics that for open system, obviously enthalpy form will be required. So, this is the correct answer. Last question goes like this: del T of E at constant volume is equals to, we are having once again 4 options. First one is CP, second one is del V of E at constant T, next one is del V of S at constant T, and last answer is CV. Okay. I think you have understood what is the correct answer. Correct answer will be obviously CV, because CV is nothing but per unit change of temperature, what amount of energy you require at constant V, that is CV. So, this is the correct answer. Hope you have got the answers correctly after reading this lecture. Thank you. In the next lecture, we will be discussing about thermal boundary layer. Okay. If you have any query, please post in our discussion forum. Thank you very much.